So, and the second problem that the enzymologist is faced with, is that identifying all these elementary rate constants that are associated with all these reactions is almost impossible when you cannot identify all these different enzyme states. So in other words, identifying which mechanism is occurring by observing these enzyme states is impossible. So the enzymologists, they had to come up with a solution, and they came up with a solution that is now called enzyme kinetics. And so enzyme kinetics it involves approximations in order to be able to study enzymes. So the idea is that we want to go from the enzyme mechanism that is described in terms of these elementary reactions. So in the simplest case, we would have something like this. And we want to, so where you have two elementary reactions, we want to write this in terms of an enzyme description in which the rate constants associated, so K1 plus, K1 minus, and K2 are no longer appearing, and also these concentrations are no longer appearing. So we want to go to a description that goes like this. So in order to do that, we need to approximate. And the field of enzyme kinetics gives you these type of approximations. So if you think about enzymes, enzyme kinetics, then there is a theory associated with monomeric enzymes. So they have a single subunit, so they're composed out of a single protein, not a protein complex, versus a multimeric enzymes. And this is a protein complex. So several subunits. Now these subunits can be identical or different, and the general case is even that these subunits are different. And this is explained in another chapter. I believe that's chapter 8. And this is chapter 6. Now there are two approximation methods. So the first approximation method is the quasi-steady state approximation. And the second one is the rapid equilibrium approximation. Sometimes called rapid binding equilibrium approximation. It depends a little bit on who you ask. And this leads to, this is a simpler approach. But also a more crude approximation. Okay, so I'm going to explain you both of these approximations on the basis of a very simple, simple example. And that's this example. So we have two elementary reactions. So V1 is K1 plus times E times S minus K minus times ES. And V2 is K2 times ES. Now, clearly, the rate of the enzyme is the rate with which product is formed. So, if we're going to take the enzyme view, so the enzyme view, which is S goes to P with rate V, there we see, okay, the enzyme rate is defined as dP dt equals V, which is minus the SDT. And this has concentration P per unit time as unit. And when we identify in the enzyme mechanism perspective what the rate of the enzyme is, so the rate of product formation is V2. So that means that the rate of the enzyme on the left-hand side is a V2, right? So, and this V turns out to be V2. But our task is now to write the rate of the enzyme in terms of enzyme parameters, so not the individual case here, so not in terms of these, but properties of the enzyme. So for instance, the Vmax and the Michaelis-Menten constant. And we also want to make sure that the rate of the enzyme V no longer refers to ES. So we want to write the rate of the enzyme that in a way that it no longer depends on ES and no longer depends on these rate constants. So that's the task. And this we can achieve in two ways. So there is the quasi-steady state approximation that works in the following way. So first we're going to discuss a little experiment. So what we're going to do, we have a test tube, let's say filled with water, and we're going to throw enzyme in it and substrate, nothing else. And the substrate concentration is going to greatly exceed that of the enzyme. Okay, so we're going to start with a lot of substrate and less enzyme, and ES and P start at 0. So now we know at the end that all the substrate will be converted into product. So we're going to make product, and we're going to lose substrate. Now, we also, something that we realize is whenever there's a product made by the enzyme is free again and can bind another substrate. And as long as you have substrate excess over product, then it's very likely that that the system, so if we do that in green, in the beginning, all the enzyme binds to substrate. And the enzyme substrate complex ES quickly goes up, stays constant, and goes down. And the reason is that whenever the enzyme is liberated from its substrate, so the product is made. Now, when product is made, the enzyme can immediately bind to substrate again because there is this excess condition of substrate over enzyme. So that means that there must exist a time window it's called the quasi-steady state time window, during which the SDT is negative, so we lose S, we gain P, but the ES dt is 0 and the EDT is 0. And that's only possible when we have an excess of S over E, because then whenever there is one product molecule formed, the enzyme, the substrate concentration is decreased a little bit, but not to the extent that less enzyme substrate complex is being formed. That means that for every product formed, immediately the substrate will bind to to E again, so that there will be no concentration changes in E, S, and E during this time window. Only when SB is depleting, and then you will see, so in this particular region, that ES goes down and E goes up. So there exists this quasi-steady state time window because S is in great excess over E. Now, the other thing that we know is that E total is E plus ES. So we have a conservation of protein because there is no net synthesis of protein or decay of protein. The enzyme is only going into different states and we regenerate it again at the end of the reaction cycle. Now, the other thing we know is that dES dt is equals V1 minus V2. We get K1 plus times E times S, K1 minus times ES minus K2 times ES. Now, in the quasi-steady state time window, we know that this equals 0. So we're going to derive enzyme kinetics in this time window, where we can consider quasi-steady state concentrations of E and ES. This relationship also holds then during those quasi-steady state conditions, and that means I can substitute for ES, E total minus ESS, now I can remove the brackets. Now I can solve for ESS. So ESS is going to equal K1 plus times E total times S divided by K1 plus, multiplied by S plus K1 minus plus K2. Okay, so this is going to be my, this is now the equation for the quasi-steady state concentration of ESS. I already identified earlier that the rate of the enzyme V equals K2, which is K2 times ESS during the quasi-steady state period. So now I can exploit that relationship too. Now this leads to an expression of V that looks like this. So I have K2 times E total times K1 plus times S divided by K1 plus times S plus K1 minus plus K2. Now, when I remove in the lower part I move K1 plus out of the brackets, I get S plus K1 minus plus K2 divided by K1 plus. And then these K2 pluses I can remove. Then I get K2 times E total times S plus K1 minus plus K2 times K1 plus. Now this constant, I'm going to use the Michaelis-Menten constant. And this constant, I'm going to use the Vmax. I'm going to call the Vmax, so the maximal rate that the enzyme can achieve. So then you get Vmax times S plus Km. Now, if I now plot the relationship between V and S, you will see it's hyperbolic for very large concentrations of S that are much greater than the Km. V equals Vmax. And where S equals Km, we have half Vmax. Now, the Vmax is equals K2 times E total. So in that particular state, when the enzyme concentration is much greater than the Km, then ES equals E total. So all the enzyme is bound to substrate. Whereas here, when you are at half Vmax, ESS is E total divided by 2. So 50% of the enzyme is bound to substrate. So that's one way. So this is now the enzyme kinetic description of the enzyme rate, where we have expressed the rate of the enzyme in terms of enzyme kinetic parameters Vmax and Km. And we are no longer considering the enzyme in terms of the K values and the enzyme substrate complexes. So now we've really achieved what we've set out to do, and that's to write the rate of the enzyme in terms of enzyme kinetic parameters alone that can be identifiable from an experiment. And we could do this under the assumption that the concentration of S greatly exceeds that of the enzyme. Then a quasi-steady state is established, during which this holds and during which the enzyme rate depends on the substrate concentration in this manner. And this equation is called the Meige-Elis-Lenten equation. And it was derived for the third time, I believe, in 1917 or so. So a long time ago, over 100 years ago. Now, the second approximation that we're going to look at is this rapid equilibrium approximation. And it makes a rather wild assumption. So it assumes that these binding reactions occur really fast and that the catalytic reaction is really slow. Such that whenever one of these slow reactions occurred, there is immediately an equilibrium is re-established here. So this is so extremely fast that it is almost, that this reaction occurs almost independently of this reaction. So whenever there is a conversion of ES to E plus P, even though this leads to a loss of ES, the concentration of ES nonetheless hardly changes because there is an immediate synthesis of ES from this side. And this means that due to this timescale separation, so due to the fact that the first reaction is much faster than the second reaction, so that means that K1 plus is much greater than K2, and K1 minus is also much greater than K2. Due to this, that continuously exists this relationship between ES and E plus S. And this is the equilibrium relationship. Right, so how do we derive this? Well, we know that V1 is K1 plus K1 minus. And if this rate is going so extremely fast that it always approximates equilibrium, then we can derive this, where the dissociation constant for this binary reaction is K1 minus divided by K1 plus. And this then leads to this equilibrium relationship. So even though these events sometimes occur, this is going so extremely fast that this relationship is nearly always approximately true. Okay, so when that is the case, then we can say, look, E total is E plus ES. and the rate of the enzyme is K2 times ES. So what we want to do, we want to solve what, we want to figure out what ES is. And then we can write down the rate equation from the rapid equilibrium point of view. So let's do that. So first we say, look, this is E times S divided by Ks. So this is E1 plus S divided by Ks. So that means that E is E total 1 plus S divided by Ks. So when you have more S, the concentration of the free enzyme goes down because you make more ES. Now we also know that, so this is the first result, at thermodynamic equilibrium, this relationship holds. And we also know that ES is E times S divided by Ks. So we can substitute this relationship. So then you get this is now the relationship for ES. Now that we can substitute in this equation. And then we arrive at K2 times E total is S divided by Ks 1 plus S divided by Ks. Now, this we recognize again as the Vmax times S plus Ks. So this looks now very similar to the Michaelis-Menten relationship before, but then the Ks was the Km. Now in the Michaelis-Menten description, the Km equaled K1 minus plus K2 divided by K1 plus, whereas Ks in this particular description is K minus divided by K1 plus. So only when K2 is small relative to K1 minus can the Km be approximated by Ks. Because you see that when you make this guy 0, then Ks and Km are the same. And this condition, so K2 being much smaller than K1 minus, is indeed exactly the condition that we assumed when we said that this reaction is way faster than this one. So that means that this value, so the K2 value, is much smaller than the K1 and minus value. And that's indeed the case. If that's indeed the case, then the rapid equilibrium approximation is an equally good approximation as the quasi-steady state approximation. But the rapid equilibrium approximation is therefore stronger also than the quasi-steady state approximation. So now if we conclude that if we have this mechanism, and we go to, and we take the enzyme perspective, then in the quasi-steady state approximation, we see that we arrive at the Michaelis-Menten equation. But if we do the rapid equilibrium approximation, then what you see is that we arrive at an equation that's mathematically identical, but Ks and Km have different meanings. Okay, so this was a very simple introduction to the essences of the rapid equilibrium approximation and the quasi-steady state approximation. And next week, we're going to continue with a few more examples, but then we're going to consider enzyme mechanisms that are more complicated and more realistic than this particular one. Okay, thank you very much.